Okay, for this section we're going to be looking at light in two different ways. First as a wave, and then next as a particle. Now when we looked at light at earlier this year, we said that light actually can behave as a wave. And there was two different ways we could prove that, and there's other ways as well. One was the double slit experiment, um, where Thomas Young took light, monochromatic light, and shined it to these two very narrow slits. The wave bent around both of those slits. That's called diffraction, generating two waves. Those two waves interfered with each other, producing bright spots and then dark spot patterns. Where the bright spots, where we could actually see the light, that's where constructive interference is going on, and then where there was no light, that was where destructive interference was going on. Another way that we can prove that light behaves as a wave is through polarization. If we pass light through a polarized filter, light is only allowed to come out in one orientation. So if we take a second filter and put that one so it only allows light to go through it horizontally, then actually no light would be emitted from the other end. And this proves also that light behaves as a wave. Now around the turn of the 20th century, we came up with a new theory of light, and this was that light can also behave as a particle. A particle of light carrying energy is known as a photon. The energy of each quantum photon is directly proportional to the frequency of that electromagnetic radiation. So through the work of Albert Einstein, we've proved that light can actually be quantized, or set to be a specific amount for an individual particle. We call that particle photon. Now, as I pointed out in the last slide there, the energy of this photon is equal to h, which is referred to as Planck's constant, times the frequency. And this equation can be found on your reference tables on page 5 under the Modern Physics section. Now, if you look on that equation in your reference tables, there's a second version of this. Well, photon is light, or a little packet of light, and light has the symbol for the symbol for the speed of light is c. Well, as we looked at earlier this year, because light behaves as a wave, the speed of a wave is equal to the frequency times the wavelength. So if I manipulate this equation around, solving for frequency, it's the speed of the wave divided by the wavelength. If I take that and plug it in over here, our second equation for the energy of the photon based on the wavelength, it is Planck's constant times c divided by the wavelength. Now h is a constant, and it's called Planck's constant, and like all constants, the equation, or the value, can be found on the front of your reference tables under the physical constant section, and that value is equal to 6.63 times 10 to the negative 34 joules times a second. Notice that's a very, 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 very small number. Now when we use this equation, the energy that we get is in joules. Dimensionally, that can be kind of seen by using Planck's constant. A joule times a second, that's Planck's constant, and then we multiply by a frequency, which is measured in hertz, or 1 over a second. The seconds will cancel out, and we're only left with joules. And when we use this equation, we get the energy in joules, but that's a very, very small number. Because this energy is so small, we typically use electron volts to simplify this amount of energy. Now an electron volt is equal to 1.6 times 10 to the negative 19 joules. It's just another unit of energy. We looked at this unit of energy first in our electrostatics unit. This relationship can also be found on your list of physical constants on the front page of your reference tables. take a look at this example. The energy of a photon is equal to 2.11 electron volts. First, we want to determine the energy of the photon in joules. So this is just going to be a conversion. Anytime I do a conversion, I start with what I want to convert, which is 2.11 electron volts. I'm going to multiply by a fraction. What I want to convert to goes in the numerator spot, and we want to convert to joules. What we want to get rid of goes in the denominator spot, and that's electron volts in this case. Based on the ratio I just gave you, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So joules will cancel out. If we put that in our calculator, we get a value of 3.38 times 10 to the negative 19 joules. Now we want to determine the energy of this photon. Well, the frequency of this photon. The energy of the photon is equal to Planck's constant times the frequency. So if I take this equation, manipulate it around, solving for frequency, it would be equal to the energy of the photon divided by Planck's constant. Now, right now, we've got two values for the energy of the photon. We have it in joules, and we also have it in electron volts. As I mentioned in the previous slide there, remember, when we use this equation, we need to make sure that the energy is measured in joules. So I'm going to use the answer that I just calculated. 3.38 times 10 to the negative 19 joules. Divide by Planck's constant, which is 6.63 times 10 to the negative 34 joules times a second. Joules cancel out. And the frequency we get is 5.10 times 10 to the 14th. 1 or a second, that's equivalent to hertz, which is our unit of measurement for frequency. Now that we know the frequency of this photon, we can determine the type of electromagnetic wave or radiation it is. In this case, it's specifically a color. If you go on page 2 of your reference tables, you should see the electromagnetic spectrum. A very small portion of that spectrum is visible light, and based on our frequency, we can determine the specific color it falls within. And that color turns out to be yellow. Now, the work done by Albert Einstein, the photoelectric effect, actually got him his Nobel Prize. And the photoelectric effect, or solar cells, is actually a principle or an application of the photoelectric effect. How a solar cell works is light needs to come down and strike the metal that it's made out of. If that light has enough energy, it will actually knock off an electron that's in the metal. And if we get a bunch of moving electrons, what we establish is an electrical current. In order for the electrons to get knocked off, though, the photon striking it, or the light that's striking it, needs to have enough energy, or basically it has to have be above a certain amount of frequency. Let's take a look at this animation here. So what I have is a light source striking this solar cell. Notice that although I have the intensity at 100%, no electrons are being knocked off, and the current is 0 here. Right now I have it at red. Now red has the lowest frequency of the visible light. So in terms of photon energy, it carries the least amount of energy. If I increase the frequency, or in this case decrease the wavelength, I'm increasing the amount of energy that's striking that surface. And if the light that's striking the surface has enough energy, or has a high enough frequency, eventually we get electrons getting knocked off of that cell there. And if I keep increasing the frequency, the photons striking this piece of metal are going to be hitting it with more energy, making these electrons pop off with a greater speed or more kinetic energy. And because they have more kinetic energy, they're going to be moving faster. In terms of current, you get this larger current. So if I increase the intensity, see right now it's at blue and it's 0.055. I keep increasing the intensity, sorry, not the intensity, but the frequency. The electrons are moving faster, and we're generating more current. So this is how a solar cell works. Now, we first viewed light as a wave based on the diffraction interference pattern. Then we proved that light also can behave as a particle using a photoelectric effect, and saying that light behaves as a photon, quantized amount of energy. Now, if waves can behave as particles, can particles behave as waves? de Broglie, physicists, actually proved that they can. What he did in 1924, de Broglie projected electrons through this crystal. Electrons being a particle. Something that we knew was a particle. The resulting pattern was very similar to the pattern produced by the famous double slit experiment that proved that light behaves as a wave. Based on this, de Broglie proved that all particles actually exhibit wave properties as well. So not only light behaves as a wave and a particle, but all objects can behave as a wave and a particle. And we can calculate the wavelength of any object by using this equation. The wavelength, lambda, is equal to Planck's constant divided by the momentum. Or momentum is equal to mass times the velocity. So it could be Planck's constant divided by the mass of the object divided by how quickly. Now, this is not on your reference tables, and you don't need to memorize it, but I do want you to kind of be aware that all objects, not only light can behave as a wave and a particle, but all objects can behave as a wave and a particle. Now, for most objects that are very big, okay, they have a very large mass, and they could be moving relatively slow. This number, Planck's constant, is a very, very small number. So if I was to calculate the wavelength of, let's say, my body moving at some speed, 2 meters per second, if I was to calculate that, using my math being, let's say, 90 kilograms and my speed being 1 meter per second, and plugging it in for Planck's constant here, I'll get a very, 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 very small wavelength. So that's why when we look at objects, we don't see them vibrating back and forth, because their wavelength is so incredibly small, therefore making the frequency very, very big.